IOE 413 Nonlinear Programming Study Guide.
Question 9. Recall the model presented in question 5, which was minimize the function x1 squared plus x2 squared, such that x1 plus x2 equals 2, 2x1 plus x2 is less than or equal to 3, and x1, x2 are non-negative. Now, I want you to write the Crush-Kuhn-Tucker conditions for a point x1, x2 that satisfies these constraints here. And note that it satisfies 2x1 plus x2 less than or equal to 3 with strict equality. 2x1 plus x2 is equal to 3 at the boundary of this hyperplane constraint. Okay? And that's important when we go to include the different gradients of the inequality functions at the end of this problem. So keep that in mind. So the first thing that we're going to do is put this problem into our canonical form by defining f of x. We've done that right here, x1 squared plus x2 squared. And then our equality constraints are written with h functions. In this case, it's x1 plus x2 minus 2. Then inequalities are written with our g functions. In this case, it is 2x1 plus x2 minus 3. And so this first constraint here, x1 plus x2 equals 2, is the same as h1 of x equals 0. The second constraint here, 2x1 plus x2 is less than or equal to 3, is just g1 of x less than or equal to 0. And then x1, x2 greater than or equal to 0, we will handle by defining the set capital X, which is the set of all x1, x2, such that x1 is greater than or equal to 0, and x2 is greater than or equal to 0. Now we have the problem stated in the canonical form that we covered in the lecture notes for a nonlinear program, and we can then move on to the next step of creating the Crush-Kuhn-Tucker conditions based on that canonical form. Now we need to compute some gradients. First, the gradient of f of x is 2x1, 2x2. The gradient of h of 1 of x is just 1, 1. The gradient of g of 1 of x is 2, 1. Let's write the KKT conditions by substituting our gradient vectors in. So the gradient of f is 2x1, 2x2 plus lambda times the gradient of h, which is 1, 1, plus mu times the gradient of g. And this is important. The reason we can include this term here is because I said at the very beginning that the inequality 2x1 plus x2 less than or equal to 3 held strictly with equality. And that means we have this term in here of mu times the column vector 2, 1. That's equal to column vector 0, 0. Then our constraints, x1 plus x2 minus 2 equals 0. 2x1 plus x2 minus 3 is less than or equal to 0. And we write it this way because that's how the Crush-Tucker conditions are written, is with the actual primal constraints reiterated here, even though in the statement of the problem we know that this actually holds with equality. We have x1 and x2 is greater than or equal to 0. And now we have this complementarity constraint mu times 2x1 plus x2 minus 3 is equal to 0. And we have that mu is greater than or equal to 0. And lambda is just somewhere on the real line. It's unrestricted in sign. So that's the statement of the Crush-Tucker conditions for this problem.